Welcome, everyone, to the IoT and IP podcast. I'm your host, Claudia Tapia, and in the company of exceptional experts in IP, business, and technology, we will explore the Internet of Things and uncover the strategies for maximizing the benefits of intellectual property rights. Let me start by expressing my sincere gratitude for you joining us today. And also a big thank you to everyone who has taken the time to share this feedback. As I often say, feedback is a present, and I love presents. One of you, Sophia, proposed an episode dedicated on the fundamentals of IoT. She said, I still do not understand how the IoT works. And it brought a smile to my face when she mentioned that a 30-minute episode might be too long. And I was thinking for myself, well, I better not mention that I originally envisioned these episodes to span an hour each. Anyway, here it goes. IoT Fundamental 101. I hope you enjoy it. And please let me know whether there are some concepts which are still not clear after listening to this episode, and I will address them in future ones. As always, you can reach me in LinkedIn and at ipwithclaudiatapia@hotmail.com. Let's start. The Internet of Things, or IoT, is a broad term describing a set of technologies and related ecosystems. In the IoT things, also known as IoT devices, communicate with each other or with servers on a network. But what is unique in the IoT is that humans are not necessarily being involved to drive such interaction. And also important for you to remember is that IoT devices interact with the physical world, for example, by measuring temperature or performing actions such as closing a door. However, to act, the IoT device must be explicitly told how to operate. And this includes how to handle unexpected situations, which might be challenging to foresee. And as mentioned in other episodes, IoT provides multiple benefits, for example, improving your health. IoT enhance the productivity in agriculture, transform industries, reduce energy consumption, foster economic growth. It enables new business models, creates opportunities for innovation, efficiency, and economic development. And this is why it's so important for you to understand how it works. And of course, IoT comes with several risks. Let's not forget that. For example, privacy concerns, security vulnerabilities, dependence on technology, or, very important also, e-waste, which we will explore in future episodes. In the context of the IoT, a thing is a device, a piece of hardware that is part of the IoT system. And these devices are equipped with connectivity features, and this is what allows devices to send and receive data over the internet or other networks. I'm sure most of you have heard smart thermostats that control and automate home heating and cooling systems. They are very useful and they help you to use energy in an optimal way. Another example is wearable fitness trackers. With those, you can monitor physical activity, heart rate, sleep patterns, and so on. If we move now to business, you can find, for example, IoT devices that track goods in transit so that companies can optimize routes, provide customers an accurate delivery estimate, and real-time updates. So in industry, you can also find smart security systems, and this includes cameras, motion detectors, door and window sensors. The industrial robots automate various manufacturing and production processes, and with them, companies can increase their efficiency and safety. I think by now you have enough examples of IoT devices. Well, many of these devices are equipped with sensors. And these sensors continuously monitor specific parameters and collect data from the environment, which can be anything like temperature, humidity, CO2 levels, light levels, location, or even motion. In other words, sensors are the eyes and ears of the system. Quite scary, yeah, but also cool. So think about temperature sensors, which measure the temperature of the environment, and you can find them in smart homes or even for industrial processes where it's crucial to maintain specific temperatures. For example, in pharma for certain drugs or in food processing to ensure the food remains fresh and is safe, or even in chemical processing to achieve the desired reaction. Another example, motion sensors. Motion sensors detect physical movement in a given area. And this is quite useful if you want to be alerted of potential intrusions, or even when passing through a corridor at the office, and then you may have experienced that you walk and then the lights are automatically turned on, and when the sensors detect you, and then when you leave, the light is turned off. And this can save a lot of energy costs, especially if you have employees like my partner, which favorite hobby is to keep the lights of the house on. And a key benefit of IoT sensors is that they can be used to monitor and report on a system parameter, such as water quality, over a long time. And with this, it can significantly reduce the cost to perform such monitoring and creating new opportunities to understand this system behavior. You might remember our episode where Øyvind Birkenes, the CEO of Airthings, explained how the devices include several sensors to measure, amongst others, the CO2 levels, temperature, pressure, and humidity. Well, humidity sensors are very important in agriculture too, to understand how much humidity is in the air. It's very important it's crucial actually to provide plants with ideal conditions for optimal plant growth. By now, I hope you can visualize some IoT devices and the sensors in them. But what happens after the sensors have collected the data from their surroundings? The data needs to be sent to a central system for processing, which is called data processing system. This data transfer is achieved through connectivity. IoT devices can connect to the internet and each other via various means of connectivity, of course, which includes Wi-Fi, Bluetooth, cellular networks, and even satellite communications in remote areas. So these connectivity options serve different deployment use cases with different characteristics. For wireless connectivity, we can separate between short range and long range for how the device connects to the network. Short-range connectivity just provides the last part of connectivity. Some of the way is needed to connect the internet, such as fiber or cellular modem. Whereas long-range connectivity allows the device to connect from wherever it is to the internet, like a cellular phone does. Okay, this might sound kind of difficult, so let me go through the different connectivity options and elaborate and give you examples, and you will see at the end of the day, you will understand everything. Let's start with Wi-Fi. Wi-Fi might be suited for high bandwidth applications with limited areas and where power consumption is less of a concern. And you might ask yourself now, what is bandwidth? Well, let me explain a bit with an example. Examples are always useful. Imagine you are at the supermarket and you're waiting at one checkout lane, and let's forget for a moment that you are convinced while you're waiting for your turn that you have picked the most slowly one. Okay, so we're now in the store with a few checkout lanes. So this means that probably you can have long queues of customers like you, and they are all waiting to pay, and they are all getting a little bit annoyed. And this, of course, causes delays. But now, ta-da! Now imagine that one or two new cashiers appear and they open new checkout lanes. Suddenly, your waiting time is drastically reduced. Well, this is similar to a network connection with low versus high bandwidth. If the network connection has a low bandwidth, data transfer speeds are slow. What happens then is that you as user experience delays when accessing websites or downloading files. Yes, we all have been there. The opposite occurs when high bandwidth exists. This means where you can access websites quickly, download files rapidly, and stream high-definition videos without interruptions or pauses for loading. And so high bandwidth, good thing. Is it clear? All right. Then I repeat what I was saying about Wi-Fi. I want to make sure it's still there. Wi-Fi might be a good option for high bandwidth applications with limited areas and where power consumption is not an issue. Examples: indoor environments like smart homes or offices where devices like cameras, entertainment system, and smart appliances need to connect to the internet and each other. Bluetooth, especially Bluetooth Low Energy, which is also known as BLE, is designed for low power consumption and short range communication. Examples: wearable health devices, healthcare sensors, and smart home gadgets. Bluetooth is ideal for simple direct device-to-device connections. For example, BLE is used to connect the fitness tracker with your smartphone and send data back and forth to your phone. Other possibilities for short-range connectivity are Zigbee and Z-Wave. They are both low-power wireless technologies designed for short, medium-range communication in what is called a mesh network. A mesh network connects each node in the network and directly communicates with multiple other nodes. So it's really good at keeping everything connected, even if something goes wrong. Do you remember when you and your friends were passing notes in class? So even if one friend left or was too nervous to be caught, and you could still pass your note to another friend until it reached the person you wanted. Well, with Zigbee and Z-Wave, everyone can stay in touch easily, no matter where they are in the room. So these technologies are primary use in home automation and smart energy solutions. By the way, Bluetooth also has a mesh node. Let's now move to long-range connectivity technologies. LoRaWAN stands for Long Range Wide Area Network. It is a low-power, wide area networking protocol designed for low bandwidth, long-range communication among IoT devices. And it can be used for agriculture sensors, smart cities, and environmental monitoring. And why? Well, because in these examples, devices need to transmit small amounts of data over long distances with minimal power consumption. LoRaWAN supports applications like urban parking spaceability, so very useful. Then we have also narrowband IoT or NB-IoT. And this is a cellular technology designed for IoT applications requiring small amounts of data, low bandwidth, and long battery life. NB-IoT is sometimes used in utility metering, smart agriculture, and environmental monitoring. NB-IoT is perfect for devices that need to send data infrequently over long distances, like soil sensors in remote agricultural fields. Next, satellite. Satellite connectivity for the IoT is like using satellites in space to send messages between smart devices all over the world, even in places where there are no phone lines or internet cables. So if you wish to track a device in the middle of the desert or in a ship in the middle of the ocean, these places are hard to connect using regular internet because there are no wires or cell towers there. So satellites float way up in space and can send signals down to these remote devices. And this way, these devices can talk to us and each other. So it is similar to how walkie-talkies work. But instead of talking from one hill to another, the message goes from the Earth up to the satellite and then back down to another place on Earth. It's super helpful for checking weather, wildlife, or even the health of crops in places that are hard to reach. And now, let's move to my favorite technology, cellular. When we talk about cellular technology, we mean the broad group of technology we use for our mobile phones, typically divided into 2G, 3G, 4G, 5G, in the future 6G. You get the idea, right? Cellular, in particular 4G and 5G, provides extensive coverage, high-speed connectivity, and low latency, meaning barely no time between transferring and receiving data. And each generation of cellular standards is built on the previous one and provides a huge improvement. For example, in 4G networks, data is transferred up to 12,000 times faster than 2G networks. And 5G brings significant improvements in speed, latency, and device density support. This means that 5G can better accommodate a large number of devices within a given area or network than the previous generation. Users still experience a great performance even when there is a high density of devices connected at the same time. Cellular is ideal for IoT devices that need to communicate over long distances or require mobility, like connected cars, smart agriculture, supply chain management and environmental monitoring, remote surgery, remote industrial monitoring, or smart city applications. In particular, 4G and 5G are used for critical communications. For example, to warn early about natural disasters like earthquakes or tsunamis. And they are also crucial when a disaster has occurred to offer secure and reliable communication channels for firefighters, for police, emergency medical services, so that they can all coordinate. It's also super useful in healthcare for example, monitoring the patient remotely in real time. And this is especially critical for patients with chronic conditions or under intensive care. Where else? In telemedicine and remote surgery, where you need secure, high bandwidth communication links that permits doctors to consult with patients remotely or conduct surgeries using robotic systems. I know, it's amazing. And this is because here you also need minimal latency so that their safety is ensured and the procedures are also effective. And cellular is also used for utilities and infrastructure, like for smart grids to distribute electricity in real time, so that there's a continuous power delivery even in adverse conditions, or for water and gas monitoring with systems that continuously monitor and control the flow and distribution of water and gas so that they can detect the leaks or failures right after it happens to prevent wastage. What else? It's also key for transportation and logistics. Talking about autonomous vehicles and traffic control, and let's not forget industrial automation or secure transactions in finance. So in all these scenarios, the critical nature of communications demands that the technologies used are not only fast and reliable, but also secure and resilient against failures, disruptions, or attacks. And this is why cellular standards, and in particular 4G and 5G, are considered key pillars of the IoT. So I think you could see that's my favorite technology, I confess. But of course, other connectivity technologies are also relevant for the IoT, and each of them has its unique strengths, making it more suitable for specific IoT scenarios. The choice between the technologies depends on the specific requirements of the IoT application. This includes the range, data needs, power consumption, and the environment in which the device will operate. By the way, there are use cases where a mix of connectivity options are the way forward. For example, industrial IoT utilizes a mix of Wi-Fi for factory floor connectivity and cellular connections for remote monitoring, or smart grids and smart retail, which uses a combination of Wi-Fi and cellular networks depending on the specific application needs. All right, it has been a lot of connectivity. I apologize, but this is really so important for the IoT. So now when you hear about Wi-Fi, Bluetooth, Zigbee, Z-Wave, LoRaWAN, satellites, cellular standards, you will know what they are talking about and for which use case might one be better suited than the other. So now we know that the sensors from IoT devices collected data, which is transferred thanks to the connectivity to the data processing system. But what happens then? After the data is transmitted, it needs to be processed. This can happen on the device itself, in a local gateway, or in the cloud. IoT devices often include actuators that respond to commands from the system to change something in the environment. In other words, when we are talking about data processing, this involves analyzing the collected data and suggesting or even making decisions based on it. For example, a temperature sensor in a smart thermostat may detect that the room temperature has fallen below a certain point, in which case the system can decide to turn on the heating. The action can be as simple as sending a notification to a user's smartphone, or as complex as automatically adjusting the controls of industrial machinery. And for this to happen, predefined rules in the sensors are needed. And these rules allow IoT devices to automate tasks and control complex systems without human intervention, making processes more efficient and responsive to changing conditions. And we are coming to the final stage. Ta-da! User interface. In the context of the IoT, you may have heard about this user interface, and this allows humans to interact with the IoT devices, check data, or manually control devices. User interfaces can be web dashboards, mobile apps, or even voice control systems. Users or the IoT device may analyze the data collected with sensors to gain insights, predict trends, and make informed decisions. For example, analyzing traffic flow data from road sensors to optimize traffic light timings, which we will all love to see. As we have learned today, the complexity of IoT systems can vary widely, from simple devices with a single sensor to complex industrial IoT systems with thousands of interconnected devices. But despite the diversity, the basic principles of collecting data, connecting devices, processing data, taking action, and interacting with users are the core of how IoT works. Thank you for joining me in exploring the essentials of IoT. I hope by now you feel more confident about the Internet of Things and how it works. Your feedback is invaluable, and I'm eager to hear your thoughts of today's episodes. Connected, we go further. Bye.